Today, let us start our session with circular waveguides and cavity resonators. So, what are the circular waveguides and what are the cavity resonators? Let us see here. In the first unit, we have seen the rectangular waveguides and we have analyzed the rectangular waveguides in different modes of propagation and different relations for phase velocity, group velocity, and what are the field expressions in the rectangular waveguide by substituting the boundary conditions we derived. Now, let us see a similar manner how the waves that are propagating through the circular waveguides and how can we construct the cavity resonators in unit 2. So, this is the second unit, circular waveguides and cavity resonators, and myself Dr. V. Vijayashree Boliseti, Associate Professor, Department of Electronics and Communication Engineering. Coming to the outcomes of this unit, at the end of the unit, the student will be able to design different modes of propagation in the waveguide structures. Same like for unit 1, we have seen for the rectangular waveguides, and in unit 2, we go through the circular waveguides. Let us see what is the contents of this unit 2. We just go through the introduction for the circular waveguides and the fields and modes of propagation and obtain the characteristic equation. Also, we determine the dominant and degenerate modes in the circular waveguides, and then we go through the cavity resonators using both circular cavities and cylindrical cavities, and what are the different dominant modes and resonant frequencies of these rectangular and cylindrical cavities we find. We also find the Q factor, quality factor, and the coupling coefficients. Also, we see some important problems in the circular waveguides and cavity resonators. Then we also go through the microstrip lines and what are the impedance relations and what is the dielectric effect, dielectric constant effect, and how these losses that are affecting the instead of using the lumped elements, why we are going for the cavity resonators, vacuum tubes. So, we see that effective dielectric constant and the losses due to this dielectric constant, and also we find the Q factor for the microstrip lines. Okay. So, these are the contents of unit 2. Let us see the introduction for the cylindrical waveguides or circular waveguides. So, myself Dr. V. Vijayashree Boliseti, Associate Professor, Department of Electronics and Communication Engineering. At the end of this lecture, the student will be able to identify the difference, what is the difference between the rectangular waveguides and the circular waveguides. So, in our previous sessions, we have discussed about the rectangular waveguides, and now let us see how we represent the circular waveguides, what are the parameters we use to represent these circular waveguides. So, coming to the introduction, basically the circular waveguide or a cylindrical waveguide is nothing but a circular conductor. Okay. So, it is just like a tube and the conduction takes place in a cylinder. Okay. So, it is a hollow metallic tube with uniform circular cross section, and so that means just simply like having a circular cross section, like this, and it is just like a tube structure. So, this is the end which is having the most important for this is what is the dimension radius r and angle phi. Okay. So, analysis of this circular waveguide requires the solution for the equation in cylindrical coordinates, and generally the parameters of the cylindrical coordinates are represented as rho, phi and z. Okay. As the propagation direction is along the z direction, we take the same, and instead of x and y axis, here we are taking the rho and phi. Okay, so this rho and phi are going to represent the dimensions, the radius and the angle with which the wave is propagating towards the z direction. Okay, so this is the circular cylindrical coordinate system representation. So the radius, if you consider, we are considering that radius is nothing but equal to a. In the rectangular coordinate system, if you take the rectangular coordinate system, the broader dimension is taken as a, and here the radius of the circular cross section is taken as a, and the propagation, if it is propagating along this direction with the z direction, the angle that is making with the z, we are considering it as phi, and in that direction, what is the plane of propagation, it is going to consider the rho. That means on the x axis element, if we consider it as rho, on the y axis if we consider it as a, on z axis if we consider the angle made by is phi. So the coordinates of the cylindrical waveguide or a circular waveguide are generally represented as rho phi z, whereas in rectangular waveguide we consider this is the direction x axis, this is the direction on y axis, and this is the propagation direction z axis. So on this rectangular coordinate system, we have the representation x, y, z, whereas on the circular coordinate system they are represented as rho, phi and z. So using these parameters, just like in a rectangular coordinate system, we have the field components like the electric field and magnetic field on x axis, y axis and z axis. So we have the field components Ex, Ey, Ez. Similarly, Hx, Hy and Hz. Here also we have the field components E rho, E phi, Ez and H rho, H phi and Hz. So anyhow, so the electric and magnetic field components along rho and phi are represented as H phi, H rho, E phi and E rho, and electric field components and magnetic field components along Z, we represent them as Ez and Hz. Okay. So now you are able to distinguish what is the difference and what is the notational difference between the rectangular waveguide and the circular waveguide, and the circular coordinate system is introduced. Now let us also go through the fields, what are the different modes that are propagating to the circular waveguide, and the characteristic equation. So in the circular waveguide also the preferred modes of propagation are TE and TM modes, just like the rectangular waveguides. Here also TE and TM modes are propagating through the circular waveguide. So let us see what are the modes that are propagating and what is the characteristic equation in this session. And myself, Dr. V. Vijayasree, Associate Professor, Department of Electronics and Communication Engineering. Let us see the outcomes of this session. And so at the end of this lecture, the student will be able to obtain the field expression in circular waveguides, and also for TE and TM modes, and what is the difference between TE and TM modes also we can see. And the student will be able to derive the cutoff frequencies using the derived expression for TE and TM, and also we can identify and differentiate what is the dominant mode and degenerate modes in the circular waveguides. So let us first see the TE wave equation in the circular waveguide. as both TE waves and TM waves propagate through the circular waveguides. So first let us see what is a TE wave in rectangular waveguide, and so from that we obtain the relation for the circular waveguides. So TE means transverse electric wave in a rectangular waveguide. So for this transverse electric wave, Ez component is 0 in the rectangular waveguide. So here also we consider that Ez component is 0, that means the propagation of electric field along the propagation direction, that is z direction, is 0 and only Hz is going to define. So let us see, for a TE wave to propagate in the waveguide, Ez should be 0 and Hz is a finite. Okay. So for this, to derive the wave equations, either TE wave or TM wave, we need the Helmholtz equation. So let us again recollect what is the Helmholtz equation that we have obtained using the Maxwell's equations. So generally the Helmholtz equation is represented as del square Hz is equal to minus omega square mu epsilon Hz for TE wave equation. Similarly for TM, we get del square Ez is equal to minus omega square mu epsilon Ez. Okay. Anyhow, let us consider this Helmholtz wave equation as del square Hz is equal to minus omega square mu epsilon Hz. We call this as Helmholtz wave equation. Okay. So now from this Helmholtz equation, let us represent what is this del square, expand this del square in circular coordinate system. So what are the parameters in circular coordinate system? They are rho, phi and z. In rectangular coordinate system, they are x, y, z. So now let us express this, expand this del square in terms of rho, phi and z. So by expanding this del square z in cylindrical coordinates, we get the Helmholtz relation is representing like this. So with respect to rho, del square can be represented as dou square Hz by dou rho square plus dou Hz by rho into d rho plus 1 by rho square dou square Hz by dou phi square plus dou square Hz by dou z square is equal to minus omega square mu epsilon Hz. Okay. Anyhow, this term dou square by dou z square, we have considered it as an operator gamma in rectangular coordinate system. Here also we consider that dou square by dou z square with an operator gamma, that is we call it as gamma square. Dou square by dou z square is represented as a gamma square, and let us rewrite the equation with gamma square. So we are going to get this dou square by dou z square is replaced as a gamma square, and if we bring this minus omega square mu epsilon to this side, we will get plus omega square mu epsilon Hz, and so the entire equation takes this form. Okay. And anyhow, we have considered this operator and omega square mu epsilon, this is gamma square plus omega square mu epsilon, as equal to h square in rectangular waveguides. Of course, here also we take it as equal to h square. Okay. So this is what the characteristic equation, and from this characteristic equation we are going to derive the cutoff frequency, and from the cutoff frequency we can find what is the dominant mode and degenerate mode. Anyhow, now first let us see what is the TE wave equation that is propagating through the circular waveguides. So let us replace this gamma square plus omega square mu epsilon as h square, and we proceed further. Okay. So this is the second equation, and we need to find the solution for this equation, and so this equation is for this equation the solution can be obtained by separation of variables, and it can be assumed to be some function of p q where p is a function of rho and q is a function of phi only. Okay. So, by using this separation of variables, let us assume the solution for this equation, that is Hz is equal to PQ, where P is function of rho only and Q is function of phi only. So, now let us substitute this 3 in equation 2 to simplify and obtain what are the arbitrary constants. So, if we substitute this 3 in 2, so we are going to get dou square PQ by dou rho square plus 1 by rho dou PQ by dou rho plus 1 by P square dou square PQ by dou phi square plus H square PQ is equal to 0. Here P is a function of rho and Q is a function of phi only. So, as Q is a function of phi only, it becomes constant. As we are applying the partial differentiation, it becomes constant Q here, and when we differentiate with rho, Q is constant, and when we differentiate with phi, P becomes constant. So, let us take these constants out of this equation and let us rewrite this equation. So, we are going to get this form, that is Q dou square P by dou P square plus Q by P dou P by dou rho plus P by rho square dou square Q by dou phi square plus H square PQ is equal to 0. Anyhow, here we have PQ is there. So, let us divide this entire equation with PQ, and if you see this expression, here we have dou square P by dou rho square and dou square Q by dou phi square, but if you divide this with PQ, again here we are having the rho term. So, let us entire equation, let us multiply with rho square by PQ, that is divide this equation with PQ and multiply this equation with rho square. So, we are going to get, multiply this equation with rho square by PQ, we are going to get this relation, that is if you multiply this with rho square by PQ, Q gets cancelled. So, rho square by P, dou square P by dou P square, and similarly when you multiply this with rho square by PQ, rho will get cancelled, Q gets cancelled. So, rho by P, dou P by dou rho, and similarly if you multiply this with rho square by PQ, rho square gets cancelled, P gets cancelled, 1 by Q dou square Q by dou phi square, plus when you multiply this with rho square by PQ, so PQ gets cancelled and rho square gets H square rho square is equal to 0. See, why we have chosen this term to multiply is so that we get, this is one term which is dependent on Q only. See, this is 1 by Q dou square Q by dou phi square, that means entire this is a function of phi only. And similarly if you observe this term, okay, so this is rho, P is also function of rho dou square P by dou rho square, and this is also a function of rho only. So, these two terms are function of rho and this term is a function of phi. So, they are independent, that means here there is no rho term and here there is no phi term, and this is rho square H square is equal to 0. So, this also depends only on rho. So, in equation 4 we have a combination of rho and phi combinations, but equation 5 we have different terms, and in this, these three terms, that is first term, second and third, if you consider, all these three terms are function of rho, and if you consider this is the fourth term, it is a function of phi only. So, in equation 5 we have 4 terms, of them 3 terms are purely function of rho and 1 term is a pure function of phi only. Okay, anyhow, so 1 by Q dou square Q by dou phi square is a pure function of phi only. So, let us find the solution for this. So, by assuming that 1 by Q dou square Q by dou phi square is equal to minus n square. So, let us assume the solution in terms of the cos and sine functions. Okay. So, the general solution for this equation 6 will be in the form of Q is equal to is equal to an cos n phi plus bn sin n phi, because it is a function of phi only, and as it depends on the term n, so we call it as it's some arbitrary constant a suffix n cos n phi plus b suffix n sin n phi. So this is equation 7. So now let us substitute this equation 6 in 5. So what is the equation 6? That means we have this minus 1 by q dou square q by dou phi square is equal to minus n square. So let us substitute that in the previous equation. So previous equation is having 4 terms. Of the 4 terms, 3 terms are the function of rho and 1 term is a function of phi. So let us substitute this in the above equation. Anyhow, we will see this in this slide. So if you substitute this 6 in 5, then the equation will take this form. That means in place of 1 by q dou square phi by dou phi square, you will get minus n square h square rho square is equal to 0. So let us see that here. So rho square by p dou square p by dou rho square plus rho by p dou p by dou rho plus rho square h square minus n square is equal to 0. So if you observe this equation is having some term p in the denominator. So multiply this equation 8 with p. So we are going to get rho square dou square p by dou p square plus rho dou p by dou rho plus rho square h square minus n square into p is equal to 0. And if you observe this equation, this is almost like Bessel's function, and if you consider this as some x and this p as some y, then simply this is actually the differentiation with rho, but multiply this with h square. If you multiply this with h square, can also write it as the differentiation also with rho h. So simply by considering this rho h as x, it is representing the Bessel's equation, and so we are going to get the solution for this equation 9 can be expressed using the Bessel's function Jn. Okay, so it is p is y is equal to some Cn Jn of x. So this is the arbitrary constant Cn, and Jn of x in a place of x we have rho h. So Jn rho h represents, it is a nth order Bessel's function. It is a nth order Bessel's function. Okay, so this nth order Bessel's function have n roots. Okay, and so by substituting, by finding those roots, we get some eigenvalues for p, and so we can obtain the solution also. So now if we get this p is equal to some Cn Jn rho phi, already we got the solution for q, that is the 7th equation. We got q is equal to an cos n phi plus bn sin n phi. So we got the solution for q, and here we got the solution for p. Let us substitute this p and q in our equation hz is equal to pq. So we get the complete solution for hz, that is hz is equal to pq, that is p is Cn Jn rho phi and q is an cos n phi plus bn sin n phi, and when we write that term in the form of some magnitude and phase component, so we get it as square root of an square plus bn square cos n phi plus tan inverse an by bn. And generally this term is this coefficient is very small, So we can also consider this n phi plus tan inverse a n by b n as simply equal to some n phi. So we can rewrite this equation as some cos n phi by considering this is, as it is small, we take n phi is equal to n phi plus tan inverse a n by b n, and this coefficient magnitude term, this magnitude term a n square plus b n square, we can consider it as a c n dash. So where c n dash is equal to root a n square plus b n square and n phi is equal to n phi plus tan inverse a n by b n. So now Hz is having some Cn and Cn dash coefficients. So together we can consider it as a single arbitrary constant, that is C naught, also as it is propagating along the z direction. So here we have introduced the rho and phi but not introduced the z component. So let us consider e power minus gamma z as it is propagating along the z direction. So finally Hg takes into the form of Cn into Cn dash, that is C naught Jn rho phi cos n phi and e power minus gamma z as it is propagating along the z direction. So this equation 11 is going to represent what is Hz, and this wave we call it as the TE wave that is propagating through the